So thank you. First, I would like to thank the organizers of this important event, of all of you, for making it happen. I'm sure it means a lot to David and his family. I have to say I'm very honored and humbled to be part of this, part of that celebration of life and work of a giant in our field, David Rowe. And I'm also honored and humbled to be a collaborator of David Rowe for several years now. Something that has admired me for a long time about David was that he has a very genuine attitude toward physics, understanding physics. He's not looking for recognitions for front seats. He's looking for understanding physics of nuclei and trying to find an elegant way, mathematical way to show this to all of us. So I'm glad that he put a lot of this in his book that he wrote together with John Wood, Fundamentals of Nuclear Models. This is the to-go books for many of us, the first book to look if any questions. I'm also here putting, I have put the latest paper that got published in Physical Review C in May 2020. I have to admit I was the referee for it, and I hope I didn't give hard time to David when I returned the report and asking him to put more of his knowledge down in print for us, the next generation, to see this and cherish it. And I think that this was a work and life of a very very good success. So let me start from where a lot of people start. The first time I met David, it was back in 2003. So this was a symposium in honor of Jerry Dreyer's 60th birthday. Jerry is my lifetime mentor and colleague, and I'm very grateful to him for learning very, very many things for physics and life. And above all, I'm grateful to Jerry for making me appreciate good physics. And naturally, this led practically to also a collaboration with David, who was appreciating good physics. So David is here on the second row. And when after that first impression of discussing and talking with him, we kept in touch. But really, the meeting that was key meeting, a very significant meeting for I would say for the research we do here at LSU. That was back at 2014, when some of us got together. You can see on the picture from the left, James Berry. He's in Iowa State University, the pioneer of ab initio models. Then Robert Baker, he's just accepted actually a fellowship at on science policy at DOE. Next to him is David Rowe. Thomas Dietrich, the computer genius for this symmetry adapted framework. Nick Sparks, currently at Tulane, a student of a postdoc with George Rosenstiel. Ali Dreyfus, currently she was a PhD student with us, currently at staff at Lawrence Livermore National Lab. George Rosenstiel, who is also not with us anymore, and Jerry Dreyer, the motivator of it all, for combining practically the symplectic symmetry with ab initio, with the ab initio framework. So we got together and we wanted to really address a big challenge back then. So we wanted to look at the 20, actually 20 particles from ab initio perspective, and couldn't even dream back then to do this because the limit was around 12 particles. So we had a lot of ideas written in the board, how to proceed with this, how to get accurate observables that compare with experiment. And this was also an important time, and I was very glad that David was part of this meeting, because the reproduction of experiment accuracy is good, but also what about physics? What can we learn something new from pushing all these supercomputers to their limits? And we did. It took us a few years, but we did. So that was the first actually ab initio calculations of that many particles. We use interactions that were only determined by few nucleon systems. And then in addition to this, we allow for all of the basis configurations to be part of the many-body model. So here it was, the symmetry was there, naturally emerging. You can see on that one of the figures here, all of this in red represents one symplectic irrep, naturally emerging from that physics of only two nucleons from the realistic interactions, or what we call first principles. Now, I want to underline, this is not a paper on discovery of symplectic symmetry in nuclei. David Rowe and George Rosenstiel did that discovery a long time ago. This is a paper where we practically said, well, if we take the best of modern day realistic interactions and we put all of the basis configurations, would this symmetry naturally emerge? And it turns out that it does. The strong nuclear force naturally exposes this symmetry, makes this symmetry in nuclei, and apparently that symmetry is quite ubiquitous in various nuclei. Now, the insight that David brought into this was practically narrated in one of his famous Spain lecture notes. And one of the figures there was very simply describing what the symplectic bases mean for us. And this is the figure here on the left, which practically says it's a coupled product of Bohr model and the AC3 rotational model. Those are these vibrations and the rotations. So as part of this, this paper, David worked very hard on the text. We constantly would go back and forth and trying to choose every word very carefully. Something that remained unchanged word by word by what he originally suggested is still in the introduction. Something that's a very, very simple concepts that tells us it doesn't matter how many observables we reproduce with a given model. If something is not right, if something is missing, one doesn't have the entire physics, and one has to investigate this and correct this, or look at to a different model that would capture all of this physics into consideration. So this is what that paper was about, and let me go back to that specific figure and tell you a little bit more detail about this. But this is a NUN 20. This is from realistic, starting from realistic interactions. We used almost the entire machines on NERSC supercomputer center, and we put everything possible, currently possible, and at the end we got a very simple picture, very simple physics. After all these complicated steps, there is this simplicity that appeared in front of us. So all this says is like, you can look at the excitation spectrum of NUN 20, the 0+, 2+, 4+, and so on. And they all have a big predominant contribution of a single symplectic irrep. and everything else there is at least an order of magnitude smaller. So that simplicity, emerging simplicity, was of a quite of a I don't think it came as a surprise. What came as a surprise is that it was really predominant. There is not small mixing that you might expect that realistic calculations could show. Now, the important part about all of this group coming together, what physics can we learn from the symplectic symmetry? And the insight that we had from the Spain lecture notes, we talked with David Rowe about this, but one can really look at the various configurations within a symplectic irrep as an equilibrium deformation. Typically, this is the deformation in the valence shell. And then we have vibrations on the top of this. This is the Bohr model. Now, this specific shape now can rotate, and by rotating can give rise of the excitation states in ion 20. And this is something that's very important for us, because now we start to understand that nuclei, at least the ones we looked so far, that they were up to the medium mass region from ab initio point of view, they all, they're made of only one or two, very few equilibrium shapes. So I put a lot of various nucleus, lithium-6, helium-8, neon-20, various of their states. You look at them and you see a big chunk in the probability on part of the wave function that belongs to a single symplectic irrep, that belongs to a single equilibrium shape that practically vibrates. And the important thing is that unless these vibrations are part of the model space, then that specific shape is not energetically favored. So larger model spaces, which is made possible by the symplectic symmetry, is crucial to get all of the deformation in nuclei from point of view of ab initio, from first principles. This also tells us a very important aspect. If we see this in the nuclei that start from realistic interaction based on, for example, in this case, Cairo effective field theory, this means that those effective interaction necessarily contain that approximate symplectic symmetry in them, and that's another work in progress. So with this, now we are able, this made possible practically for us to go and study intermediate mass nuclei, something that hasn't been possible for a long time. And this is our, again, first ab initio prediction. Here they're shown as dots, they're extrapolated value, but for the first time there is no effective charge. So everything is starts from ab initio picture and does not use the effective charges. And they compare nicely to measurements that have done in Triumph. These are shown here compared to those measurements for another set of BOV2 values. And while the various other models, they're based on valence shell with effective charges, there is also another ab initio that again, it will need effective charge in order to reproduce the experimental value. So with the symmetry adapted concept, now we're able to utilize, so we're utilizing the work that David practically devoted a lot of his life to make possible to describe for the first time to BOV2s, collective transitions in this way. So something that I want to point out is that one of the best historical overviews I have seen for the symplectic or the emergence and use of symmetry in the many nuclear model was contributed by David Rowe to the book that recently appeared, Emergent Phenomena in Atomic Nuclei from Large-Scale Modeling. That's a symmetry-guided perspective. It included contribution from various talks from QCD to light nuclei ab initio and heavier nuclei too. But David very nicely, starting from the Elliott AC3 model, the rigid Roder model, introduced in this article the symplectic model, the symplectic shell model, and various aspects and features, and how historically people have arrived at different models, capturing some of the physics and trying to understand the complete physics that rules nuclei. So I want to highlight few studies here that would not have been possible without David Rowe's work. Of course, one of the seminal papers on oxygen-16, where single symplectic EREP was used to reproduce the states, very challenging for shell model calculation states in oxygen-16, and this is work that also with Cairo Barry, for example, and Ali Dreyfus, we were expanding with a different type of interaction to, for example, carbon-12, the Hoyle state, and neon-20. So in this case, I'm showing the example of cluster wave function that one can calculate using the symplectic symmetry. So all of this, it's very much, we need the symplectic, the norm, the key matrix for the symplectic basis. We need all of the symplectic generators, matrix elements. All of this, it's something that was made available to us. And without this, none of this would have been possible. So the interesting part now is that since we have cluster wave functions, so these are the function, the wave functions for the two clusters that form inside neon-20, we can now, with this knowledge, study, for example, nuclear reactions. And if we know the reaction rate for alpha plus oxygen-16 that would form neon-20, then one can also use this to look to the stars, right? To start to understand stars and stars explosions and all of the nuclear energy that fuels these explosions. But before this, let me just point to the interesting fact, how now, for the first time from point of view of microscopic shell model calculations, we can take a look inside of nuclei like oxygen-16, the second 0+ state, and see how clusters emerge from it, very different than the ground state itself, which is very much a spherical distribution. So these are one-body probability, one-body density profiles for both oxygen-16 from microscopic wave functions that are calculated in the symplectic model. So having the nuclear reaction, we can really look at astrophysical processes. And one of my favorite studies, for example, the impact on X-ray burst abundances. This is when we have two stars. One is a neutron star, very dense star, and there is a material accreting from the other star, showing in the picture. And there are a lot of nuclear reactions that's happening and fueling this process. And practically they can change the abundances of the elements as we in different models. So using the reaction rates that I just the wave function that I just showed and calculating the reaction rates, we can study this. And really, with this type of models, we can start from untangling nuclei to glimpsing at the stars. And one last highlight that I wanted to point to is we can go the other way around to study the most fundamental model. This is the standard model, and using nuclei, using symplectic symmetry that is very critical, for example, to get the right energies and cluster wave functions for beryllium-8 that is made of 2 alpha clusters. And in this case, this was critical for describing the decay of lithium-8 to beryllium-8. And because this decay is informative of the weak interaction, there was experiment that has been recently performed. And through ab initio calculations, we provided to them some of the needed matrix elements. And with them and with the data they got from the experiment, they arrived at the most stringent test to date about the weak interaction and the tensor current contribution into the weak interaction, which was found consistent practically with the standard model. So again, none of this would have been possible without David's work, and specifically the one that is on the symplectic sp3r symmetry. So thank you, David, for the abundant knowledge you bestowed upon us, the next generation, and the generations to come, for giving us a chance to untangle elusive physics, and for your seminal work on symplectic sp3r symmetry for nuclei. And as we say in Bulgaria, may his memory be eternal. Thank you all.